Hi class, in this first video of the narrated PowerPoint for chapter 11, which is where we are going to discuss liquids and solids, I'm going to discuss some properties, some important characteristics that actually make a solid or make a liquid. So what are the key differences between solids, liquids, and gases? There are some things that you probably know from school, but just to make sure everybody is on board with that idea, I'm still going to take some time to kind of relate to that information. Recall from General Chemistry 1, where we first talked about gases. So in chapter 5 of your book, we discussed gases, and one of the key things about gases was that the molecules in gases are far apart from each other. So let's say you have a sample of gas, you have a molecule here, you have a molecule here. The distances between the molecules are just way too big. They're in fact way too large as compared to the actual volume of the particles itself. So one can say that primarily the volume of a gas is because of the intermolecular distances rather than the volume of the material itself. When you compare that to a liquid, let's see what happens. In case of a liquid, you would see that the molecules would be somewhat closer. So you can perhaps envision that for the same volume, essentially the particle density is going to be higher. And now if you compare that to a solid, those will be tightly packed. Those would be so tightly packed that there's absolutely no room for any movement of molecules. And so one can envision that the case of gases, molecules can tumble around, they can move from position A to position B, so there's translational motion involved. In case of a liquid, that motion, that movement is somewhat curtailed because the intermolecular distances are a little bit smaller, whereas in case of solids, there's absolutely no room for translational motion. The only possibility of any kind of movement is essentially a vibration about an axis, and that's about it. And we'll discuss this in a little bit greater detail for those of you who have to take organic chemistry. We'll discuss that again in a little bit more detail. But realize that because the gas molecules, because the gas particles are kind of oblivious to the presence of each other, they act independent of each other. The attractive forces or repulsive forces between two particles are going to be negligible. Particles are absolutely free to move in what we then called a random motion. So I don't know if you remember or not, but just to make sure everybody's on board again, when I say random motion, I mean that the molecules are going to be moving in different directions, and they would have different speeds associated with it. So the length of the arrow gives you the magnitude of the speed, and the direction of the arrow gives you the direction in which the molecule is moving. And in case of gas samples, this is going to be completely random. And we say that liquids and solids, both of those have different properties than gases, and they actually have stronger forces of attraction between particles. So we can no longer say that molecules are absolutely oblivious to the presence of each other. So, just to kind of put a face to the picture, if you consider gases, molecules are far apart. This is like, somebody living in North Dakota or Wyoming or, Alaska. You don't have many neighbors. You just keep driving. You don't find any neighbors. Compare that to liquid. That will be like the population density in a place like Orlando, for example. And if you compare that to maybe the population density in India or China, when you can't walk there, it's like jam-packed, too many people together, that will be something like solids. So realize that liquids and solids, molecules are going to be closer to each other. They're going to feel the presence of each other, and we're going to study how that's going to differ, how that's going to relate to the properties of solids and liquids for that matter. Another thing that basically decides how well or what kind of properties the solids and liquids would have is what is called as polarity. So what do we know about polarity from General Chemistry 1? Recall that polarity depends on electronegativity. So first we need to know what is electronegativity. Let's change the color. What is electronegativity? On your periodic table, and I'm just going to kind of draw like a and then like that. On your periodic table, you have the left side, which is where all the metals are. You have the right side, which is where all the non-metals are. And in General Chemistry 1, we said that a greater difference in electronegativity. So if the difference in electronegativity, En is for electronegativity, if that is large, then we can safely say that it is going to be a polar bond. So polar bonds do require the presence of a greater amount of a difference in electronegativity. That means that maybe one of the combining atoms would be from, something like carbon, and there would be another one which would be something like fluorine. So that would be considered a polar bond. Now one might consider, well, what would happen if you have a metal combined with a non-metal, because metals are supposed to be electropositive. Their electronegativity is really, really low. And if you compare that to a non-metal, what kind of polarity would that be? Absolutely, that would be a very highly polar bond. But also recall that a metal-non-metal bond is an ionic bond, actually. Metal non-metal bond it has a greater level of ionic character. So if you're considering a covalent bond, first off, you must have the bond between the two non-metals, but within that, the difference in the electronegativity is going to be stark. It's going to be gigantic. Over here, I'm showing you an example, which is methyl chloride or chloromethane. Notice I have 3 CH bonds. Recall from General Chemistry 1, your teacher should have told you that if you have a hydrogen and you have a carbon on the Pauling scale, which is what we use to measure the electronegativity, hydrogen is at 2.1, carbon is at 2.4. So the difference of electronegativity is not much. So anytime you have only carbon-hydrogen bonds, you pretty much consider that part or that segment of the molecule as nonpolar. On the other hand, on the Pauling scale, chlorine is 3.2. So now between 3.2 and 2.4, there is a difference of electronegativity, which is why we say that the electronegativity, or the electron density rather, that is shifted more towards chlorine. So you can envision this to be similar to like tug of war, where chlorine is going to be the winner. It's pre-decided. We already know that chlorine is going to be the winner in that game because chlorine is the big guy. So chlorine, because it attracts the electron density towards itself, chlorine attracts electron density. It gets a negative charge. And where is it getting that electron density from? It's getting that from carbon. That renders carbon a delta positive. Now you might wonder, what is this delta? This delta just means partial, just means small. Partial or small. That means the chlorine has a slight negative charge, or a carbon has a slight positive charge. It's not a full negative or a full positive charge. So it's just a tendency that we are saying. You can perhaps see that in this electron density map also, that the top portion of the CH3Cl, that's very red. And more red it is, that tells you that there is greater electron density. The bottom half of this, that is pretty blue. That means there is a dearth of electrons in that segment of the molecule. How else can we depict this? We can depict that using this arrow which is pointing towards chlorine. So the base of the arrow is at carbon, the arrowhead is at chlorine, and that basically tells you that chlorine is the negative end of what is called as the bond dipole. So you would say, if somebody asks you, is chloromethane polar? You would say absolutely it is polar. And the reason for that is the presence of this bond dipole that exists in the molecule. So what have we learned so far? We have learned that for anything to be polar in nature, we need a difference in electronegativity. If you have something like carbon, hydrogen, it automatically is considered greasy and nonpolar. Also recall, I'm going to erase parts of this so I can write more. Recall molecules which are homonuclear. So something like hydrogen bonded to hydrogen or Cl bonded to Cl. These are considered nonpolar. The reason why they are considered nonpolar is because the extent with which one atom pulls the electron density towards itself, same as the extent that the other atom pulls the electron density back. So the net effect is that the electron density doesn't go anywhere. There is no push and pull. So we consider these kind of molecules, H2, Cl2, N2, all the diatomics basically, we consider those as nonpolar. Just a quick thing, so you can remember all the diatomics. No fear for ice cold beer. No fear for ice cold, COL, so that's for chlorine, beer, that's bromine, and hot peppers. Hot peppers. So N2, O2, F2, I2, Cl2, Br2, and H2. Those are my diatomics. Anytime you see a diatomic molecule, that automatically means that it's going to be non-polar in nature. It has to be homonuclear though. Something like HCl, that too is, it contains two atoms, but those are not homonuclear. One is hydrogen, the other is chlorine. And in this case, you would say that the Cl is going to pull the electron density towards itself, and that bond will be polar, absolutely. So one might question, is there like a quantification of this? Can you actually put a number? And absolutely, if the delta En, if the electronegativity difference is more than equal to 1.7, we just consider it an ionic bond. If that number happens to be less than 1.7 and more than 0.5, so if it happens to be more than 0.5 and goes up to 1.7, so like a number like 1.4, 1.2, 0.8, all of those are polar covalent bonds. When it's less than 0.5, we just consider that non-polar. All right, so I introduced this term bond dipole, which causes a bond to be polar. And if such a polar bond is present in a molecule, in a covalent molecule, there is a good likelihood, there is a good chance that that particular molecule is going to be polar as well. But there is one other parameter, there is one other feature that you have to test to be able to make a call whether molecules on the whole are polar or not. So there are two different things. One that we called a bond dipole, which is basically evaluated by looking at the difference in electronegativity, and if that difference in electronegativity happens to lie between 0.5 and 1.7, more than. Then we would say that this would be a polar bond. Now, the other feature that I'm talking about is the shape of the molecule, the geometry of the molecule. Let's say you have something like CO2, carbon dioxide. If you draw the Lewis structure based on the Lewis theory that you learned in Gen Chem 1, you would say that carbon has 4 electrons around it. Each of the oxygens has 6. Let me change the color for that. Here's 4 and here are 2. The other oxygen as well. I'm going to probably even show oxygen in blue so you can see the difference. And so hopefully you can envision that there are 1, 2, 3, 4, 5, 6, 7, and 8. Total 8 electrons around carbon. There are total 8 electrons around oxygen and 8 around the other oxygen. Now, on the Pauling scale, the value for electronegativity is 3.6. 3.5 to 3.6, and carbon is 2.4. So the difference between the two is 1.2. So yes, definitely, most definitely, this oxygen is going to pull the electron density towards itself, but so would the other oxygen, and by the same amount. So you would say that the extent with which the electron density was pulled towards the first oxygen, it's the same extent that the second oxygen pulls the electron density towards itself, and hence CO2 together as a whole is non-polar, even though it does contain polar bonds. So the answer to the question, does it contain polar bonds? Yes, it contains polar bonds. But that does not necessarily mean that the molecule is going to be polar as well. Why? Because in this case, because polarity has a directional sense, it has a vector effect, it has a directional sense, the extent of the pull of the electrons by oxygen is nullified by the presence of the other oxygen. So one can say that the requirement for polarity is, yes, you should have the difference in electronegativity, and the geometry should be such that they don't nullify. The dipoles don't nullify, don't negate each other. Negate each other. Or you can say that if you have an asymmetric molecule, when I say asymmetric molecule, that means that if you have maybe on one side you had oxygen and perhaps on the other side you had sulfur, that would mean that the extent of the pull on one direction is not exactly opposite to the other side. So if the length of the arrow is not equal, one will definitely would be able to say that overall the molecule is going to be polar as well. So again, keep in mind, bond polarity is a requirement. Bond polarity stems from the difference in electronegativity, and if the molecule is symmetric, then they will negate each other, and overall there will be no molecular polarity. On the other hand, if it's an asymmetric molecule, then yes, you would see bond polarity culminate into the polarity of the molecule. And so one can say that the net sum of the individual bond polarities, because they have the sense of direction, they are vectors after all, that is what decides whether the molecules themselves are polar or not. Over here, I have an example that we discussed earlier as well. The bottom part of the molecule is pretty greasy because all you have is CH molecules. There's only one bond here which is polar, and that is directing towards the chlorine, and that would make the CH3Cl very highly polar. If you compare that to maybe CCl4, where it's a tetrahedron which is being pulled in all four opposite directions. In this case, whatever is the pull that is felt in this direction is going to be nullified by the resultant in the opposite direction, and hence you would say that that is not going to be a polar molecule. All right, so let's take a quick look at whether we can quantify this polarity or not. Yes, polarity can be quantified in terms of what is called as the dipole moment. It's denoted by the Greek symbol mu, and it gives us an idea of polarity. You can say greater is the numerical value of the dipole moment, greater is the polarity. So greater mu implies greater, higher polarity. Mathematically, it is determined by determining the product of the charge and the distance of separation of the charges. So in that sense, you can perhaps envision that the SI unit would be coulomb for charge, meter for the distance of separation. So coulomb meters is what the units are going to be, which is also referred to as dBi. The conversion factor is 1 dBi equals 3.336 times 10 to the power of negative 30 coulomb meters. This Q usually would be in terms of the unit charge. So 1.6 times 10 to the negative 19 coulombs is the charge of an electron. And so depending on whether it's 1 positive, 2 positive, you would be able to make your call whether you need to multiply it by 1 or 2 or 3 as the case may be. But definitely greater the value of the dipole moment, higher will be the polarity. So if I say that water has a polarity of 1.84 dBi, so that's for water, and I say that ammonia, it has a polarity of maybe 0.78, and I ask you which one is more polar, you would say water is more polar for the higher value of the dBi units. Okay, based on the dipole moment, you can also determine the percentage ionic character. So far in General Chemistry 1, your teacher must have told you that if you have a metal-non-metal bond, it's going to be always ionic. If you have a non-metal bond, it's going to be covalent. So it's pretty clear cut. We are taking it one step further. Even within all the ionic bonds, it's a possibility that the difference in electronegativities is, let's say, 1.7 or 1.8. It's like kind of borderline. How do we, or where do we draw the line then? How do we tell what is the extent of the ionic character? So that is dependent, that is measured as a percent ionic character, which is determined by first calculating the experimental value of mu. So that's an experimental value that an experiment would be run to determine that. And then we would plug in the calculated theoretical value of the dipole moment and determine that percentage IC. A higher value of percentage ionic character would mean that that bond has more is more similar to an ionic bond. On the other hand, if you have a real low value, that means it will behave more so like a covalent bond. Let's work on an example. We have HCl, hydrochloric acid. That means it's HCl aqueous. And so you have H and Cl, which hopefully would break. And if they do, then you should have an H plus and a Cl negative. The question is that you have to determine the percentage ionic character. The data that is given is that the distance between the atoms is 127 picometers. That basically is your bond length. Experimentally measured dipole moment is 1.03 dBi. Recall from the previous slide, I said that the percentage ionic character is equal to experimental mu divided by calculated mu times 100. This experimental value is given to be a 1.03 dBi. If I am able to determine the calculated value, I would be able to determine the percentage ionic character. In order to get the calculated dipole moment, which is nothing but the product of the charge times the distance of separation. Since it's a unipositive, uni-negative charge, the Q is going to be 1.6 times 10 to the negative 19 coulombs times the radius is 127 picometers. Pico means 10 to the power of negative 12. So you can safely say that this value comes out to be 2.032 times 10 to the negative 29 coulomb meters. We also learned earlier that 1 dBi is equal to 3.336 times 10 to the power of negative 30 coulomb meters. So now I would want to convert the coulomb meters that I have just gotten. I would want to convert that into dBis so that I'm comparing the experimental value in dBi to the calculated value in dBi, comparing apples to apples. So now I would need to basically divide the number that I have got. I need to divide that by the value that we just wrote for the dBi. Let's make room somewhere. So I'm just moving it up over here. 2.032 times 10 to the negative 29 coulomb meters. I'm just writing the whole 9 yards so you can see for yourself how you can use the dimensional analysis method in case you forgot about it from General Chemistry 1 again. 1 dBi. The coulomb meter and coulomb meter got cancelled. This conversion factor will be provided to you. Don't have to memorize that. That value will be provided to you in the formula sheet in the test, but you should know how to work around that. Realize since my value was in coulomb meters, I used the coulomb meter part in the denominator, and I want the final value in dBi, so I put the 1 dBi as a numerator. Now I'm going to work out the math for that. So on your calculator, you should be dividing 2.032 times 10 to the negative 29 by 3.336 times 10 to the negative 30. And I'm getting a value of 6.04 dBi. So that is my calculated mu. So let's plug in those values. 1.03 dBi divided by 6.04 dBi times 100. dBi and dBi will get cancelled off. So I'm dividing on my calculator. I have punched in 1.03 divided by 6.04. And that gives me, times 100, gives me 17.1% as your percentage ionic character. So one more time, just to make sure everybody is on board with the idea. If you're able to calculate the percentage ionic character, you can basically claim whether the bond has more ion-like properties or ionic properties, or whether it's more covalent. And greater is the value, that would mean that it has a greater tendency to stay as ions. In this case, the data that is given to you for hydrochloric acid is that the distance between atoms is 127 picometers, which basically means that it is 127 times 10 to the power of negative 12 meters. Since it's HCl, it means it would be unipositive, uni-negative. So your charge is going to be 1.6 times 10 to the negative 19 coulombs. When you multiply, carry out the math, the value you end up getting is 2.032 times 10 to the negative 29. And we divided it by 3.36 times 10 to the negative 30 to convert it into dBi so that I compare that value to the experimental value of 1.03. And that's what I plugged in the end for the percentage ionic character, which came out to be 17.1%. All right, let's work on another question. The question is, which of the following compounds are likely to have a dipole moment? Show the direction of each. So that's a great question because you're able to essentially plug in all of the information that we have discussed so far. You would be able to put that in perspective. So a couple things here. The first one that we have is SF6. I would suggest that you should draw the Lewis structure and the VSEPR theory that you learned in General Chemistry 1. SF6, sulfur has 6 electrons around it, and fluorine has 7 electrons around it. So each of the fluorines is going to surround the sulfur in an octahedral shape. Whatever is the extent of pull in one direction, so for instance, fluorine is going to pull it in one direction, the fluorine in the opposite direction is going to pull it back. So you can perhaps envision that an octahedron is basically a very regular shape. So even though you do have, bond dipole in this case, you really don't see or will not see a polarity, an overall polarity in the molecule. So this is not going to have a mu. The mu is going to be 0. It's nonpolar, even though the SF bond is polar. So it's the effect of the geometry that you're seeing, that the extent of pull on one side is going to get nullified by the effect on the other side. Consider CHCl3. That's going to be a tetrahedron based on the VSEPR again. The top part of the molecule is going to be pretty greasy, so this is a nonpolar end. Whereas the bottom part of it, where you have the 3 chlorines, yes, you will see polarity. And the net polarity is going to be essentially in a direction, which is the resultant of the three vectors. So it will be a net downward pull. Okay, and so this will have a mu, finite mu. CH2Cl2. Cl. So hopefully you can see that this part of the molecule is pretty nonpolar, and the CCl bonds are going to be polar. So the net effect will be in this direction between the 2 chlorines, and so this too will be a finite mu. CH2 double bond CH2. So that's your molecule. All it contains is CH bonds. That means it's pretty greasy. All of these bonds themselves are greasy and nonpolar. So if the bonds themselves are nonpolar, there's no reason for me to even check the shape of the molecule. So this will be mu of 0. So the only 2 that will show a bond or are likely to show some dipole moment are chloroform CHCl3 and dichloromethane CH2Cl2.